Hello, this is Michael Bell from the International Research Institute for Climate and Society at Columbia University. And this presentation covers how to use the IRI data library to calculate correlations and lagged correlations. The presentation should take about 40 minutes or so. The Pearson product moment correlation quantifies the linearity of the relationship between two variables. If no linear relationship between two variables exists, the value of the correlation is 0. If there is a perfect positive linear relationship between two variables, the value of the correlation is positive 1. If the relationship is a perfect negative linear relationship, the value of the correlation is -1. A small absolute value of the correlation does not necessarily mean that there is no meaningful relationship between the two variables. The relationship may just be nonlinear. Additionally, correlation does not imply causality. A strong correlation between two variables might be found even if no physically meaningful relationship between the two exists. In the data library, the Pearson product moment correlation is calculated using the correlate function. The arguments of the function are the two variables being correlated and the grid over which the correlation is being calculated. In this example, there is an estimated precipitation data set from the Climate Prediction Center, and it's being correlated with another gridded precipitation data set from NASA. So you have the two data sets listed there, and then you apply the correlate function, and you see that the time grid T is within the square brackets. The gridding of the two variables being correlated must match, or one must be a sample of the other. If the gridding of one variable is a sample of the other, then the correlation will be calculated for only the overlapping portions of the grids in the two data sets. In other words, over the grid points that are common to both variables. Now, a lagged correlation is just the correlation calculated between variables that are offset in time or space, for example. It may be useful, for instance, to investigate whether there is a relationship between two variables that are offset in time, especially if a cause-effect relationship is suspected. Lagged correlations can be calculated in the data library by applying the shift data short command on one of the variables and then using the correlate command. The shift data short command has the following syntax. First, you have the variable that is to be shifted along the grid. The grid is named grid, so you use the name of the grid here. Then low is a number that designates the lower limit of the number of grid steps to lag the variable with respect to the original grid. Step is a number designating the grid step interval to use when shifting the variable. The default value is 1. High is a number that designates the upper limit of the number of grid steps to lag the variable with respect to the original grid. And then you use the command shift data short. When shift data short is applied to a variable, a new lag grid is created and applied to the variable. This new grid has the name grid_lag, where grid is the name of the original grid along which the variable is being shifted. So for example, if you have a time grid named capital T and you're shifting along that grid, then the new lagged grid would be called capital T_lag. This new grid holds the values of the variables in their new positions along the original grid according to the size of the lag that is applied. So how shift data short works is best demonstrated with an example. So here consider a variable containing a series of 7 numbers along a time grid capital T running from January 2001 to August 2001. Now if the command T-212 shift data short were applied to this variable, it would then also depend upon a new grid named T_lag and would have the following structure shown here. Additionally, the T grid for the variable will be shortened to include only those time steps that have data values in all 5 lags. In this case, March 2001 to June 2001, which is the unshaded area shown in the figure here. So the larger the number of lags you use, the shorter the time grid T will become. At 0 lag, which is T underscore lag equal to 0, the variable has its original orientation along the time grid. For a positive lag of a single time step, where T underscore lag equals 1, the values of the variable are moved backward with respect to the time grid by 1 time step. In other words, the original value for April 2001 becomes the value for March 2001, and the April 2001 point gets the value originally assigned to May 2001. By applying the shift data short command in conjunction with the correlation command, one can immediately calculate lagged correlations for multiple lags all at once. So to continue this same example, suppose the values in the previous table are to be correlated with another time series of the same length for lags -2, -1, 0, 1, and 2. So here we have our first series, which has been lagged at all 5 lags, and now we're introducing a second time series that also runs from January 2001 to August 2001. And we want to correlate these two series at the various lags. When correlating these two series, the correlation will be done using only the March 2001 to June 2001 values in both series, because of how Series 1 was shortened by the multiple lags. The result of the correlation between these two series will be a set of 5 correlation coefficients, 1 for each lag, and the results at each lag are shown here. So let's do an example, and in this exercise we'll use shift data short to calculate the lagged correlation between TRIM monthly precipitation anomalies and monthly malaria incidence anomalies by subzoba in the country of Eritrea for 1998 to 2003. So subzobas are districts in Eritrea, and so we'll be correlating the malaria incidence anomalies with precipitation anomalies. So here's the list of general steps that you would go through in the data library expert mode to do this kind of a calculation. First, you would select the first variable, calculate its anomalies, then transform and or restrict the time and spatial domain to match that of variable 2, then select variable 2, calculate its anomalies, and again transform or restrict the time and spatial domain to match that of variable 1. Then you would apply shift data short to the second variable to shift it in time at various lags with respect to the first variable. Then you would correlate the two variables by applying the correlate command. And just as a template, this is how the series of commands would look. So we'll go through all of these steps in detail for this example. So by calculating malaria incidence anomalies and TRIM precipitation anomalies for subzobas in Eritrea, we're removing the influence of the annual cycle from both of these variables. And so we can explore the possibility that these variables covary in a linear fashion by calculating the correlation of the monthly anomaly values. So the reason we want to remove the anomalies is that, or the reason that we want to calculate the anomalies is that there may be a lot of correlation between two variables simply because they follow the same or a similar annual cycle. And so we're not so interested in the influence of the annual cycle itself. We're really more interested in how the two variables might covary in terms of their anomalies, or how they might covary in terms of differences from the annual cycle. So we'll start by placing the expert mode calculations of the Eritrea malaria incidence anomalies by subzoba and TRIM precipitation anomalies by subzoba into the same expert mode text box. And when you do so, this is what the set of commands in expert mode would look like. Here we select the malaria incidence values. We calculate their anomalies using yearly anomalies. Then we select the trim precipitation data, and we restrict that data to a region over Eritrea by using the X and Y range commands. We also restrict the trim data to the period January 1998 to January 2004, and we calculate monthly averages. So in this case, the trim data are originally daily, but we want to use monthly values so that we can match them with the monthly malaria incidence values. Then we calculate the anomalies of the trim data, and then we overlay the subzoba district regions, and we use the weighted average command to calculate spatial averages of the trim precipitation values over the subzobas. So in this way we have precipitation anomalies for the subzobas to match up with malaria incidence anomalies also for the subzobas. So if you look at the result on the Data Library Expert Mode page, and you look at both the district and the t-grids, you'll see that the two variables match. Actually, the time grid of the trim dataset is a subset of the time grid in the Eritrea malaria dataset, since trim begins in 1998. Now, to examine correlations between malaria incidence anomalies and trim precipitation anomalies, leading and lagging by up to 4 months, you would simply include the following two commands. So you would use T -4 1 +4 shift data short to apply the lag and lead, and then you would use the T correlate command. Then you would click OK, and to quickly visualize the result of this calculation, you can click on the Colors Data Viewer icon, and that will display the following figure. And what you see on this figure is, along the horizontal axis, the names of the districts or subzobas in Eritrea. You don't see all of them here just because of a lack of space. And then along the vertical axis you see the time lag going from -4 to +4. And what you see in general is that the highest correlations tend to occur at the -2 and -3 month lags. Those are the areas with the red and with the most red and orange colors, and that's the highest correlation. So low correlations are in blue, high positive correlations are in yellow, orange, and red. So as I mentioned, the color plot Okay, so this is part 2 of the lagged correlation presentation. I'm going to skip forward through some of the slides and start part 2 here on slide number 21. Okay, so I'll start now. So when you click on the Colors Figure Viewer option, you should see a plot that looks something like this. And we'll go through the next few slides and talk a little bit more about it. So the color plot shows correlations between trim precipitation anomalies and malaria incidence anomalies by subzobas, and those subzobas are listed along the horizontal axis, versus lag from -4 to +4 months along the vertical axis over the period for which the correlation is calculated, 1998 to 2003. And negative lags indicate the number of months by which trim precipitation anomalies lead malaria incidence anomalies. So when precipitation comes before the malaria incidence. And so you can see these on this plot. You can see the names of the subzobas or districts in Eritrea along the horizontal axis. You don't see all of the names just because there's a lack of space here. And then you see the lags in terms of months from -4 to +4 along the vertical axis. In terms of the colors, the yellows, oranges, and reds indicate positive correlations, and the blues indicate negative correlations. And specifically, colors from yellow to red indicate increasingly positive correlations, and colors from light green to blue are increasingly negative correlations. And since shift data short was applied to the trim precipitation anomalies, the negative lags signify precipitation leading malaria incidence, and positive lags signify precipitation lagging malaria incidence. And in the figure, the generally modest but increasingly positive correlations for many subzobas in the -2 to -3 month lags appear to support the idea that positive precipitation anomalies tend to lead by 2 to 3 months the positive malaria incidence anomalies in many of the subzobas in Eritrea during 1998 to 2003. It's also generally true that the negative precipitation anomalies would tend to lead the negative malaria incidence anomalies by 2 to 3 months. And if you're interested in seeing the actual values of these correlations listed, rather than just seeing them plotted on a figure like that, you can click on the tables link on the expert mode page to see a table of the numerical values. Now we could also find the correlation between malaria incidence anomalies and some other variable of interest, such as the Normalized Difference Vegetation Index, or NDVI, which might be used as a proxy for rainfall. And once we found an appropriate NDVI dataset, we can use essentially the same procedure that we used for the trim precipitation to find the lagged correlation between NDVI anomalies and malaria incidence anomalies. So an NDVI variable that covers Africa and overlaps the data period for the malaria incidence, in other words January 1996 to December 2003, is the USGS NDVI-G dataset. And it's found here at Home, CIPH, USGS, NDVI-G, Monthly Maximum, DEG 0P1, NDVI. So this is a dataset of monthly maximum NDVI for Africa, and it's gridded at a 1/10 of a degree latitude-longitude resolution. And given the size of the subzobas in Eritrea, this resolution is fine enough so that we can produce subzoba average NDVI anomaly values. In other words, the pixels for the NDVI data at a 1/10 of a degree resolution are fine enough to be resolved within the shapes of the Eritrea subzobas. So here's the next exercise. Use shift data short to calculate the lagged correlation between monthly NDVI anomalies and monthly malaria incidence anomalies by subzoba in Eritrea over the same period, 1996 to 2003. And here are the steps you would go through. Again, you would select the malaria incidence data, calculate the incidence anomalies, select the NDVI data, including whatever restrictions you need to make in the temporal and spatial domains, then calculate the NDVI anomalies. Then select the Eritrea subzoba shapes dataset from the data library. Then use the weighted average command to calculate the subzoba average NDVI anomaly values so that you'll match up with the malaria incidence anomalies. Then you would apply shift data short to the NDVI anomalies to shift them in time at various lags with respect to the malaria incidence anomalies. And then correlate the two variables by applying the correlate command to the time grid. And so this is what the full script would look like in expert mode. We select the malaria incidence anomalies, the malaria incidence values, and calculate their anomalies. Then we select the NDVI data from 35 east to 45 east and 10 north to 20 north, over this time period from 1996 through the end of 2003. Then we calculate the monthly average of these values. We need to put them on a monthly time step. They're originally on a decadal or 10-day time step. And then we calculate their anomalies by month. Then we select the shapes of the Eritrea subzobas and apply the weighted average command. Then we apply the shift data short command and then apply the correlate command to the time grid, capital T. And to quickly visualize the result of the calculation, you can click on the Colors Data Viewer icon, and that will display the following figure. So this looks fairly similar to what we saw for the TRIM precipitation correlations with the malaria incidence. Again, you see the names of the subzobas across the horizontal axis, the lags across the vertical axis. But the distribution of the correlations on the figure itself are a little bit different. And actually, it's a little more interesting to talk about the spatial variations in the correlations rather than the temporal variations. And so we'll come back to that later by looking at a map. So rather than just displaying a lag versus subzoba figure or a table of the resulting correlations, we can create a map of the correlations over Eritrea in the data library as well. So next we'll go through the procedure for mapping a variable that is a function of shapes, such as administrative boundaries that are available as a data set in the data library. So here's the general procedure for mapping variables by shape geometry in the data library. And in expert mode, mapping a variable by shape geometry requires 3 input streams, and they need to be in the following order. First of all, you need to select a background gridded data set with sufficient spatial resolution to resolve the shapes of the size you're using. And the sources world bath data set will typically work. The resolution of that data set is fine enough. And you should spatially restrict that data set to the region of interest. In other words, find a box, in our case around Eritrea, and restrict the sources of world bath data set to that spatial domain. This will be sort of a skeleton upon which we put our map. We're not going to be mapping this variable itself. Next, we select the geometry variable, in other words, the underscore geom variable of the shapes to use in the map. And then third, we designate the data that we're going to place on the map. And these data should be a function of the grid that indexes the shapes. And in our case, it's going to be, well, GID. So the index of the shapes must match the index that we use to indicate what subzobas we're mapping on the map. And once those 3 elements are in place, the next step is to generate the figure itself using the fig colon construct. And an example of this command in expert mode is the following. So we have xy fig white mask fill by black thin solid districts underscore gas fig. So we'll go through each piece of this. So the x and y indicates that we are creating a map in longitude and latitude. So x is longitude, y is latitude. Those are the axes of the map that we're creating. Then we need to include the fig colon construct, and within the fig colon construct we first put white mask, and that masks out the world bath elevation data set that's serving as sort of a skeleton for the map. We're masking out the elevation data because we're not actually using that data. then we use the word fill by. That fills the district shapes with a color representing the result of the calculation on the district data. So fill by is going to fill in the district shapes with colors that represent, in our case, the correlations. Then next, in this example, thin solid districts underscore gas overlays district outlines on the map. And the thin and solid are parameters that describe the lines that we're using for the district outlines. So we're making thin solid lines on the map for the districts. Then we end the set of commands with a :fig. And that's the information that we need to display the map. You can put that information into expert mode, or you can also go to the edit plot page and enter this information there. So to map the NDVI and malaria incidence anomaly correlations by subzoba, follow this procedure. Place the expert mode code for the world bath gridded dataset spatially restricted to the region around Eritrea and the Eritrea geometries before the code used to calculate the lagged correlations in the expert mode window, and then add the figure : code that we just went through to create the map image. Then you would click on the viewer link to enter the figure viewer and access the control above the map to view correlations at different lags. So here's the script. It's a bit longer than the others. At the beginning you can see we select the sources world bath dataset, and we select a latitude longitude domain, and in fact in longitude we're going from again 35 east to 45 east, and in latitude from 10 north to 20 north. Then we select the shapes of the subzobas. That's the geom variable. And then the rest of the information here is up to the correlate command is just the correlation that we did in the previous exercise. So this is where we're correlating the malaria incidence anomalies with the NDVI anomalies. And then at the very end we have x, y, fig : and this is where we input the figure information that we just described a moment ago. Okay. So once you've input this expert mode code, click on the viewer link to enter the figure viewer and access the control above the map to view correlations at different lags. And you'll see that at various lags the correlation between the malaria incidence anomalies and NDVI anomalies tends to be most positive in the semi-arid subzobas in the north of the country. So when you create the figure, when you use that expert mode code that we just saw and click on the figure viewer, you'll see something like this. Here we're seeing the 0 lag. You'll see there's a control at the top of the map where you can select the various lags available. It goes from -4 to +4. Here we're looking at the 0 lag. In other words, when the NDVI anomalies and malaria incidence anomalies are happening at the same time. The correlation color scale is similar to what we saw before. Increasingly blue values are increasingly negative correlations, and colors that go from yellow to red are increasingly positive correlations. And you can see that the very highest correlations tend to be in the northern semi-arid zone of Eritrea. Okay, so this is the conclusion of the lagged correlation presentation. Thank you for listening.